The last thing we're gonna end with today, when we do ramp questions where it's like an inclined plane, like a triangle, sometimes you're like, I want to use forces and kinematics, or sometimes you're like, I want to use energy like we just did. But the classic example of a roller coaster when it's kind of a, ooh, that's not a good track, but let's do this. The classic example of a roller coaster when you have like a curved surface, that's probably a pretty good indication that you're going to want to use energy, just because we never did forces questions. We never did force questions when we did a curved surface, and eventually we'll do the circular motion and it gets a little bit more involved. But if you ever see a kind of a curvy roller coaster thing and you have a block, and let's just say there's no friction in here, boom. Let's say it starts at a height, and I'm going to give you numbers, but it's not super important, because remember we're going to use my variables. Just like this. Boom. And this is a little side profile of a roller coaster here. And we're just going to find some things. This is super cool. I want to know how fast it's going at, let's say, I'm not going to draw this to scale. Let's say that's a height of 5 meters. Not drawn to scale. I'm not a great artiste. And then let's say, I don't know, let's say a height of 3 meters right here. Boom. And then how fast is it going at a height of 0 meters? Okay. And first things first, when you're looking at this roller coaster, they might say rank where it's going the fastest. Well, think about that for a second. What does it mean to be going the fastest? You've used up all of your potential energy. Well, where do you have the minimum potential energy? It's when you have the maximum kinetic, right? So you're going to be going the fastest, boom, right here, because you have 0 potential, all kinetic. Then you'll be going the next fastest right here. According, technically you have different spots on here, but of the points we're looking at here, you'll be going the fastest here, the next fastest here, the next fastest here, and you'll be going the slowest right there because you have all PE right there, or the most PE right there, right? So just keep in mind, when PE is low, then your KE in a problem like this will be high, okay? And your PE is low and your height is low, okay? And your KE is high when your velocity is, I'm going to put V, your velocity is high, okay? It's a V. All right, so we have that. So let's just do this. Let's call this point A, we want to know, and let's call this point B, and let's call this point C, just like that, okay? So what I want to do, I'm going to use energy concepts to say how fast you're going at point A. All right, so find the velocity at point A. So step one, I always say, can we use the conservation energy? And I say 0 equals E final. And we'll call this part A. We're looking for the velocity at A. Okay, so as you're going down the roller coaster, and so here's the deal, E final minus E initial, just like that, equals 0 joules. I'm telling you right now, we have no friction acting in our system. We have no person pushing the roller coaster. The only force is a conservative force. It's gravity acting on our system. And keep in mind, it doesn't matter. I know it's weird. If you had a block fall from 10 down to 5, or you had a block go from 10 down to 5 and it kind of went a curved path, because we're ignoring friction and gravity is a conservative force, a block that goes 10 down to 5 this way or a block that goes 10 down to 5 through a curvy path, the big difference is it fell a height of 5 meters and its PE transformed over to KE. So technically, if we're ignoring friction, those two objects would be going the same velocity because they've fallen 5 meters in the y direction, in the vertical direction there. Okay, so let's identify this here. The final energy, boom, at point A right here, it's still up in the air. So it has potential energy, mgh final. Okay, and I call it final just because I'm looking at my system from point here, initial, to final right here. All right, but now here's the thing. At point A right here, it has potential energy, but you ask yourself, so it's got PE, right? PE final. I'll just put PE, but it's also moving, so it has KE right there. So I'm going to say the final energy at this point right here, it has PE, but it also has kinetic energy, and I'll put final. That's your energy at point A, and just like that. And I'm keeping in mind that I'm solving for velocity at point A, that's what I'm calling my final, even though I know I'm going to do more in the question. Minus, what was the initial energy that it had at the very beginning? Well, they could have this up in the air, so it has potential. They could have this up in the air and moving, so it has potential and kinetic. I'm going to start a little more simple. I'm just going to say it's up in the air, so it's all PE to start. Okay, so I'll say PE initial. Put finals on here just to kind of keep track. Okay, so we say initial energy. I'm just going to say this object, it was up in there, mgh initial. Okay, if it were moving, you'd have to include a kinetic energy term right there, but I'm going to say it wasn't moving, equals 0 joules. Okay, so we have this right here, and there's a great reason to solve this in variables, and so I'm going to keep it in variables because it'll help us later on, just like this. So mgh final, so I'm going to say mgh final. And actually, you know what? I'm just going to rearrange this. Oh, I'll show you the steps here. Plus 1/2 mv final squared minus mgh initial equals 0 joules. And then you're like, well, Laurent, we got to solve for the final velocity. I'm going to take these terms over to the other side. mgh initial minus mgh final equals 1/2 mv final squared. Just like that. And I have an m in every term, so that's going to cancel. And then one other thing, I'm going to factor out a g on this side. So I'm going to kill off the m's. It's mass independent here. It depends on the height that it was raised, and it depends on the height that it's going to. So I'm going to say g h initial. And you can call it h sub 0 if you want. I don't know why I started using an I again, but minus h final equals 1/2 v final squared times by 2 on both sides to get that over. Times by 2. And then if I'm looking for v final, I take the square root of both sides. Square root. So it's kind of cool. V equals the square root of 2g and the difference in the heights. And then I actually just call that delta h, the difference in heights, hi minus hf, just like that. All right? And you might look back to that example we did before, and you're like, well, that's what I got for the ramp. Velocity is the square root of 2gh. You're right, because however far you fell, that height in the y direction, that contributes to how fast you're going. Then if it's a bigger height that you fell from, then you're going to be going faster at the end. And one little thing here, we didn't call this a delta h because you started at some height h and you went down to 0. And keep in mind, it's not a scalar, so you don't have to put a negative h or anything like that in there. Well, in this case, you fell from some initial height 10 down to 5. So 10 minus 5 would be 5 meters it fell. Okay, so the reason why it's kind of cool is when you go to do your math here, velocity at A, it's just going to be, boom, velocity at A is square root of 2. Gravity, we call it 9.81, call it 10, I'll call it 9.81 meters per second squared. Remember, energy is a scalar. You don't have to go mess around with negative numbers. 10 minus 5, so that'd be 5 meters. And you punch this through, it's about 50 squared. It's going to be about 10, right? So 5 times 9.81 times 2 equals square root of that. You get about 9.9 meters per second. And actually, if you're rounding, made it like 9.91, but let's call it the velocity at A. And one thing, you know that's not the top speed of the roller coaster because you know that's only when it's falling 5 meters. The top speed is going to be quite a bit faster at the bottom right there. Okay? Now, you might be like, we did that in variables. Why'd you do that? Well, you don't have to go back and redo everything because you know the velocity at B. Look at all the work you're going to save yourself. The velocity at B is going to be the square root of 2g, still hi minus hf, hi minus hf. Well, in this case, if you're at velocity at b, your hi is still 10, minus your hf, which is 3, so it's 10 minus 3, which will be 7. So velocity at b will be the square root of 2g times 7 meters. Being lazy. So you do, what is that going to be? 7 times 2 equals times 9.81 equals square root, second answer. So now you're going 11.71. So velocity at B is 11.71 meters per second. Makes sense. You should be going faster because you've used up more potential energy. You have more kinetic energy right there. All right? And then the velocity at C, and look at all the work you just saved because you didn't have to redo all that because you did variables. The velocity at C, square root of 2gh, final, hi minus h final. So hi was 10 minus 0, 8, just like that. So it's going to be 10 meters. I'm really getting lazy. That's 10 times 9.81 times 2. 10 times 9.81 equals times 2. Square root, second answer. I get about 14 meters per second. Velocity at C equals 14.01 meters per second. And that makes sense because at the very bottom, all my energy is in the kinetic energy term, and there's 0 potential energy left. So the cool thing is about this is that it's the difference in heights that matter, because the big thing is you can do velocity A, B, and C pretty darn quickly just using the conservation of energy.